Bonding. We're going to cover specifically valence bond theory, not the only explanation for how molecules bond, but a pretty good one. So with valence bond theory, we're going to look at single bonds, double bonds, and triple bonds, but essentially any of these covalent bonds we are thinking of as being formed when orbitals overlap. So you can imagine if you had a hydrogen, it would have one electron in its 1s orbital. If you had another hydrogen, it would have another electron in its 1s orbital. When those two bond together, they're going to be sharing that orbital and putting one electron from each atom into that orbital, and they're going to be more stable because of this, and that is going to form that bond between them that we represent with our Lewis diagram as a single line. So we're thinking of it as these individual hydrogens with their 1s electron around them in a spherical shape. They're able to bond and form a molecule which has a new orbital where both electrons exist in that shared area around those two nuclei. And one would have one spin, one would have the other. Again, doesn't matter which one has which, as long as when they're together in a shared orbital, they have opposite spins. So this we'll call end-to-end overlap. It'll look a little bit more sensible when we're dealing with a p orbital. But the name for this is a sigma bond. And so essentially when we have a end-to-end overlap, two orbitals overlapping, we're going to refer to that as a sigma bond. You can think of that as a single bond for now. So let's say we had beryllium. Does it have enough orbitals to overlap to join onto two hydrogens as it does in the case of BH2? So we know this molecule actually exists, so we need to figure out, okay, well, how is it able to do that? And then carbon, same problem we have here when we actually look at the bonding of it. We have carbon forming 4 bonds, which we know it loves to do, but how does it do it? What we're going to see is that just leaving carbon's energy level diagram, the placement of its electrons as they are when it's a lone atom, we can't really explain how it gets to 4 bonds, because if we look at it, so let's say we were to draw carbon's energy level diagram. So we've got our 1s orbital, our 2s orbital, and our 2p orbitals, and carbon having 6 electrons, 1, 2, 3, 4, 5, 6. So if you looked at carbon and said, okay, if I'm going to share some electrons with some other atom in a shared orbital, this one here and this one here are the only orbitals that have a carbon electron in them that have space to share with other atoms' electrons. So based on that, carbon could only share 2 orbitals. And if it can only share 2 orbitals, it could only form 2 bonds. Clearly, it doesn't do that. It forms 4 bonds all the time. So how does it do that? And we're going to explain how it does that using this idea of hybridizing the orbitals. So let's look at beryllium first as a simpler example. So beryllium has 4 electrons around, and you'd think beryllium would be stable and not react because it doesn't have any orbitals to share. Its 2 valence electrons are sitting together in that 2s orbital. So really it shouldn't be able to form any bonds, but it does. So our job is to explain, okay, well, this is the reality. It does. That's the evidence. How can we explain that using our models? And so this is where we use hybridization. So we need to explain 2 bonds. In order to do that, we need 2 half-filled orbitals from beryllium so that it can share them with hydrogen. So if we were to use one of the p orbitals with the 2s orbital, and if we were to combine them together, and let's move that 1 electron into this empty p orbital, then we would have 2 orbitals, each with an electron in them. That could be how it forms these 2 bonds. So this is what we do. This is called hybridization, is where we take previously existing orbitals and we combine them in a way to explain the bonds that we see in molecules. So this s orbital, which is no longer just an s orbital, and this p orbital, which is no longer really a p orbital, they are now on this, they're like a new subshell, or a new sublevel, and we're going to call that an sp subshell, and you can call it a 2sp if you want. But the important part is that this allows us to put the electrons in a way that explains how it can bond with hydrogen. Because now, if hydrogen were to come along, hydrogen with its one electron in its 1s electron, it could put that electron into that orbital. And a different hydrogen with its 1s electron, that's our 1s, it could share in this other orbital. And then we could have our beryllium bonded to a hydrogen, bonded to a different hydrogen with those shared orbitals between them. So in order to explain how BeH2 exists, we have to do this hybridization. These unused orbitals, if you don't want to draw them, that's fine. In order to explain the bonding that we see in BeH2, we don't need to use them, so if you just leave them out and just talk about the 2sp hybridized orbitals, that's fine. So another molecule that exists is boron trichloride. So boron forms 3 bonds with 3 different chlorines, and that molecule exists. So if you look at boron's energy level diagram as it is, there's no real explanation as to how it can possibly get 3 different shared orbitals with chlorine without hybridizing its orbitals. So if we need 3 bonds, we're going to need 3 half-filled orbitals. So if we take the s orbital and 2 of the p orbitals, so I'm going to use a superscript to say, okay, I took 1 s and 2 of the p orbitals, and then we move the electrons and spread them across that sublevel, we will end up with a sublevel with 3 half-filled orbitals in it, where we can share from the chlorine, we can share 1 electron right there, the other one can share right there, and the other one can share right there. So we end up with a way for this molecule's structure and the way it bonds to be explained through hybridization. Since we took an s orbital and we took 2 p orbitals, we call this sp2 hybridization. And again, we're not using that other p orbital. You don't need to draw it. This is what we want to focus on, the orbitals involved in the bonding of the molecule that we're trying to explain. All right, sp3 hybridization. This is where carbon fits in. Clearly, carbon forms 4 bonds, but how does it do it? It must be through the hybridization of its s orbital and all of the p orbitals. Take the electrons that it has, it's all of its valence electrons, spread them across that new hybridized subshell, and then we have 4 possible half-filled orbitals where these 4 hydrogens would each be able to put 1 of their electrons, forming those 4 bonds. And again, because we took our s orbital and our 3 p orbitals, we call this sp3 hybridization. So we use these hybrid orbitals to explain bonding that we see in molecules. We know the molecules exist, we know they're stable because they are existing. We need to be able to explain how they form the bonds that they do in order to exist. So hybridization, if you're taking these and you're sort of bringing up that 1s energy level, you can think of this requiring energy, but because you're forming all of these bonds after doing so, the molecule itself as a whole is going to achieve overall lower energy and therefore be more stable because of that hybridization. So hybridization also allows the valence electrons that are lone pairs as well as bonded pairs to exist at the same energy level. So if we see water, if you look at oxygen's energy level diagram, you'd assume, okay, well, it's got 2 lone pairs, it's got 2 half-filled orbitals. We know it forms 2 bonds when it's forming water, so it doesn't look like it needs to hybridize. But it does hybridize. And so if you look at oxygen, here's its energy level diagram as it is an atom. So you'd say, okay, well, there's a half-filled orbital, and there's a half-filled orbital. I could just take hydrogen's electron, put 1 there, take another hydrogen's electron, and put it in the other one, and that should do it. But for a couple of reasons that this doesn't happen, and one of the reasons why we know it doesn't happen, because if oxygen had these p orbitals around it, they would exist on the x and the y and the z axis. And so if a hydrogen were to bond on one of them and a hydrogen were to bond on the other one, okay, sure, maybe that happens, but this would be a 90-degree angle, which would mean water should have a 90-degree angle, and it doesn't. It doesn't have that shape. So we know that this is not what happens. Instead, what's happening is it's got a tetrahedral shape to it. It's almost as if it's a tetrahedral with a hydrogen here, and let's draw the other hydrogen here, but because of the lone pairs, this angle has actually been reduced, and so it's down to 104. So it's like a modified tetrahedral structure to it. And what that means is that the angles of these guys have got to be pretty close to what a tetrahedral one is. So it's as if we're dealing with 4 orbitals that are all pretty equal. And this can be explained if we think, okay, well, it does sp3 hybridization. Even though we don't need to do that to explain the bonding, it does explain the geometry of the water molecule. If the lone pairs and the bonded pairs are all on the same subshell, then it makes sense that water's angle is not 90, like it would be if they were on their original energy level diagram. Instead, they're a modified tetrahedral shape because all 4 of those are sp3 orbitals. The lone pairs and the bonded pairs are all on the same energy level. There's also sp3 hybridization, where we're bringing in a D subshell. And so where we have 5 bonds forming, like phosphorus pentafluoride, we're going to need 5 half-filled orbitals. So if we look at phosphorus in its ground state, we've got a lone pair and we've got 3 bonded pairs. So this explains why phosphorus often forms 3 bonds. But occasionally it forms 5 bonds. So in order to do that, we're going to need 5 half-filled orbitals. We're going to need an S, 3 P's, that'll give us 4 bonds, but we need 5. So it must be also including a D hybridization. So that we call this sp3D hybridization. And you can imagine when we have 6 bonds forming, it's going to be the same idea, but we're going to need that S. We'll take all 3 of the P's, that'll give us 4 orbitals. A D would give us 5, but in this case we have 6, so we must be using 2 of those D's, hybridizing them, spreading the electrons across all 6 of those orbitals, giving us the opportunity to form 6 bonds. The shapes of these orbitals, again, we have the most probable area to find the electrons are going to be found in these particular shapes. We have S is a spherical shape, as we know. P is sort of this double lobe shape. And when they get hybridized, so when we have an SP hybridization, whether it's SP, SP2, or SP3, they're going to look like this. So you can think of them as having one big lobe and then one little lobe. So we're doing this very similar to a p orbital in terms of shape, but we're going to sort of imagine them as having one big lobe and one tiny lobe. Double and triple bonds are created when these p orbitals overlap side to side, and we're going to call this a pi bond. So we have our sigma bond, which is an end-to-end overlap, and we have our pi bond, which is a side-to-side overlap. And we'll see what that looks like. So a double bond is going to be made up of 1 sigma bond and 1 pi bond. A triple bond is made up of a sigma bond and 2 pi bonds. If we form a double bond or a triple bond, we're going to be using p orbitals. And if they are to be p orbitals, they have to be left unhybridized. So when we see double bonds or triple bonds, we're going to need to leave our p orbitals unhybridized. So when we get a molecule that has double or triple bonds, we've got to think, okay, well, how is the energy level diagram going to look for this? We know if we have a double bond, we need a p orbital. If we have a triple bond, we're actually going to need 2 p orbitals to get that triple bond to form. So imagine we have a carbon atom in C2H4. So if we draw a quick Lewis structure for it, we're going to see that we've got our carbon, and we've got to fit 4 hydrogens. So let's put one there, spread them out pretty evenly around it. Each carbon has 4 valence electrons, so that's 8, plus the hydrogens, 9, 10, 11, 12. So we've got to place 12 electrons. So let's put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've got 2 more to place. The hydrogens don't want any more, so there must be a double bond between these 2 carbons. So there's a good Lewis structure for our C2H4 here. What this means is we've got these sigma bonds that are going to be attaching the carbon to the hydrogens and the carbon to the carbon and the second carbon to these hydrogens. But if we're going to form a double bond, it is made up of 1 sigma bond and 1 pi bond. So we're going to figure out how to make that pi bond there. Carbon's normal energy level diagram is going to look like this. This gives us, this is its hybridized energy level diagram. We have taken one of the p orbitals and we have brought it down with another one of the p orbitals. So we've got our s and our 2 p's. That's our sp2 hybridization. If we were forming 4 single bonds, we would have brought the other one down. But we're going to leave this as a unhybridized p orbital because we're going to want to make our pi bond with that. This pi bond right here is going to have to be made with an unhybridized p orbital. So we've got sp2 and we've got a normal p orbital that we're going to use to make that pi bond. So if we were to draw a valence orbital diagram, this can help us to conceptualize or to picture what this is going to look like. If we see our carbons, let's do the same colors here. So our carbon and our carbon, and so our hydrogens here, hydrogen, 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 clean up this. Now, hydrogen, it has its electron in an s orbital. So you can imagine that looks kind of like a sphere. This hydrogen looks the same. This hydrogen has its electron in a 1s orbital. This guy has its electron in a 1s orbital as well. So that's fine. These orbitals for our carbon are sp2 orbitals. So let's draw them in purple. So we've got 3 sp2 orbitals around each of the carbon atoms. And they're going to be what's bonding to these hydrogens. So let's draw that one first. Remember, our hybridized orbital looks like one big lobe and one little lobe. And that's actually labeled that. And that's sp2 orbital. So that's going to allow the hydrogen to bond to the carbon. That is a sigma bond, end-to-end overlap. Our other hydrogen down here is going to have to be bonded with the same thing. So let me draw one of those two. One, zoop, and an sp2 orbital. So let's say that's this guy right here we've drawn, this guy right here we've drawn, and they are sharing their electrons with the hydrogen. So imagine a hydrogen with a 1s electron. It's hydrogen, that's a 1s. One of them's going right there and sharing, and that's what we're seeing on the top hydrogen. A different hydrogen also has a 1s electron, and it's sharing in the second sp orbital. Now the third one that I'm going to draw here is going to share with the other carbon, because as we saw with our Lewis structure, they are also bonded together. So that would be another sp2. So that was our third sp2 orbital for that carbon. So that's the setup for, let's call it carbon A. I'm going to catch up and draw the same setup for our second carbon, also using the sp2 orbitals that it would have. I don't have the energy level diagram drawn for it, but it would be the exact same as the first carbon. they are bonded to each other, the two carbons. That's a sigma bond. You can kind of see why they call it an end-to-end overlap. It's less easy to see when it's a sphere, but when you have these hybridized orbitals, end-to-end makes sense as the name of a sigma bond. So that would hold the structure together. But there is also, let's get the blue out here, there's also this pi bond. And so this pi bond has to be explained as well. And the valence orbital diagram helps us to visualize how that works. This p orbital is how we're going to do it. If carbon A, this carbon right here, wants to share electrons with this other carbon, they're doing that. So they've got this single sigma bond in the middle here, that works. But if they want to share a second pair, so if it's a double bond, they've got two pairs of electrons they've got to share. This middle space is already occupied. So if they want to share another one, they can't do it in the space between the two atoms. But if they have a p orbital, what they're able to do with that nice linear double-lobed p orbital is they are essentially able to share that second pair of electrons above and below the bond that's in the middle. So this allows them to sort of reach around the one in the middle and still share that pair of electrons, which allows them to form that pi bond. There's a messier diagram, especially when they're on top of each other. So again, the pi bond overlaps in two places. So we need a p orbital to do it, and that is why we left our p orbital unhybridized in our energy level diagram. That's why we would have been doing sp2 hybridization, so that this unhybridized p is able to reach around the sigma bond in the middle and form that second bond, that pi bond. We call that end-to-end overlap, and realize, yes, they're overlapping in two spots. That counts as one single pi bond. If we had two carbons and two hydrogens, if we went to draw the Lewis structure for this, we'd have a carbon and hydrogen. So if we try spreading them out, that's as far as they can get. Each carbon will contribute 4 valence electrons, each hydrogen 1. So that is 10, 2, 4, 6. The hydrogens are happy, so we can't put any more electrons there. 8, 10. So the Lewis dot diagram would suggest that we have a triple bond. And so we can imagine that is going to be a sigma bond plus 2 pi bonds that makes up that triple bond. And if we are to make 2 pi bonds, we are going to need 2 unhybridized p orbitals. The sigma bonds, the one holding onto the hydrogen and the one that joins the 2 carbon, that can be made with our sp hybridization. So if you want a carbon to form a triple bond, you're going to need 2 p orbitals, and then the other sigma bonds around it can be made with sp orbitals. So if we were to try to draw this, essentially, here's a big mess here, but essentially we'd have a carbon bonded in the middle, and it would use a sp orbital to attach to the hydrogen, and that would give us a sigma bond. It would use another sp orbital to attach to the other carbon, and that would give us another sigma bond. The second carbon, let me just double over the same work. I don't have the energy level diagram for it, but it would be the exact same as the first one. It'll overlap with this hydrogen, and that's a sigma bond. So that's this sigma bond, the middle sigma bond, and the other sigma bond connecting to the right hydrogen. Now, if the space between the 2 carbons is already taken up by that shared pair of electrons, the only other option would be to reach around it, and a p orbital would be needed to do that. So you can imagine a double-lobed p orbital and a double-lobed p orbital would be able to reach around the middle and share. That would form our first pi bond. So the middle is taken up with a sigma bond, the top and the bottom are taken up with the first pi bond. The second pi bond would be with 2 other p orbitals, 1 on each. So we use 1 for one pi bond, and we use the other p orbital for the first pi bond. If these guys here have this other double-lobed p orbital, and this one has it running on the same plane, then they can share another overlap around and form a second pi bond. So essentially think of it again in terms of the planes. The linear plane right through the middle is taken up with a sigma bond, and then this particular plane right here, and it's going to get messy, this is going to be able to make one other bond, which is our first pi bond, and this plane right here is going to be able to overlap between the two and share electrons, and that'll form our second pi bond. So that is going to be as many electrons as you can fit between 2 atoms, and this is why with molecules you're limited to a triple bond, because we've taken up the middle, we've taken up the top and the bottom, and we've taken up the left and the right, or the front and the back, if you want to think of it that way, and that's pretty much as close as you can get those electrons to be, so you're not going to be able to exceed a triple bond. A coordinate covalent bond is where you have a bond forming from something that has no electrons. And again, that seems a bit odd. How could a hydrogen ion bond to a ammonia molecule if it itself doesn't have any electrons? And the way it's able to do this is it uses nitrogen's lone pair and says, okay, I see your lone pair there. I don't have any electrons. Let's share that lone pair. And essentially you end up with a hydrogen bonded to the nitrogen in the same way the other hydrogens are, but the overall structure ends up with a positive charge. It's short 1 electron because again hydrogen showed up to the party without an electron. But because of the charges, it is able to share that pair of electrons with nitrogen and form a covalent bond. The name for that would be a coordinate covalent bond. Same thing's going to happen with a hydronium ion. When a hydrogen ion meets water, it's able to do the same thing. It's able to share that lone pair with the water molecule.